let's consider normal PDF. Xi's are normal with mean mu and variance sigma square. So we already know that MLE, again, let's say we have a random sample of size n. And we already found that mu hat is x bar and sigma hat square is square summation xi minus mu, not mu, sorry, x bar whole square divided by n. Okay, so let's check. These are unbiased estimators of mu and sigma square. Or the question is this one: find unbiased estimators of mu and sigma square using mu hat and sigma hat square. Okay, so let's first look at the expectation of mu hat, which is expectation of x bar. Okay, so it's already mu. So x bar is an unbiased estimator of mu. So we don't have to find a function of that. Immediately we found it. Okay, so let's find the expectation of sigma hat square. Okay, so to be able to do that, we need to use some predefined distributional sampling distributional knowledge. So here, what we know about, so our starting point is normal, okay, and we know that summation xi minus x bar whole square divided by sigma square distributed as what? Do you remember? Chi-square with n minus 1 degrees of freedom. We already proved that. Okay, in the sampling distribution section. So here we want to find the expectation of summation xi minus x bar square. So let's try to find, let's put that so we don't have to find the distribution of summation xi minus x bar square here in terms of expectation. And using this basically, then expectation of xi minus x bar whole square divided by sigma square as n minus 1 degrees of freedom of the chi-square distribution. So this means that expectation of summation xi minus x bar whole square equals to sigma square times n minus 1. Okay, but sigma hat square has n term in it. So this means that expectation of summation xi minus x bar whole square, n is just constant. So we can do sigma square n is minus 1 over n. So actually, as you can see, this is not directly equal to sigma square. So this means that MLE of sigma square is not an unbiased estimator of sigma square. But we can obtain an unbiased estimator of sigma square because we have this constant term, right? If we write this constant term inside of the expectation, then we keep sigma square alone here. Then we can find the unbiased estimator of sigma square as a function of sigma square. Okay, so expectation of, so this is our sigma hat square. If you multiply it by n and n minus 1, sigma hat square will be sigma square. Okay, so as a function of sigma hat square, n over n minus 1 sigma hat square, or summation xi minus x bar whole square divided by n minus 1 is an unbiased estimator of sigma square. Okay, this is the end of the question. Okay, so let's consider another example. Okay, uniform example. Remember, from 0 to theta is positive, and again let's assume that we have a random sample of size n. And if you remember here, we found the MLE by inspection, not differentiation. MLE of theta hat obtained as nth order statistic. Okay, so the question is MLE of theta an unbiased estimator of theta. If not, find an unbiased estimator theta in terms of nth order statistic. Okay, so our question is to check the unbiasedness. We have to find the expectation of nth order statistic and then check is equals to theta or not. So to be able to do that, we need to find the distribution of xn and then find the expectation. Okay, so I hope you remember how to find the PDF of nth order statistic, f of xn and f to the xn to the n minus 1. There's a formula, remember? We have different approaches to find this one. I like the easiest one for me to use CDF approach. If in the CDF approach, definition of CDF is probability that xn, the maximum value, less than or equal to some lowercase xn. So if logic is this one, if the maximum of the observed all random variables is less than some number, then this means that all of the random variables should be less than that number. And using the independence of sample, then we can write this probability as a multiplication of n xi less than or equal to this given as lowercase xn. So it gives us the nth power of the CDF. And taking the derivative will give us the PDF. I hope you remember it. So here we have n 1 over theta. If you remember the CDF of xn, or if you just get the CDF here. Okay, so from 0 to xn 1 over theta dxn. So xn theta. Take the n minus 1 power of that. Okay, so we have xn to the n minus 1, n times theta to the n, and the range of xn from 0 to theta. Okay, so let's try to find the expectation. Then we already found our PDF. So from 0 to theta, xn, and write PDF. dxn. Okay, so n to the theta to n out, and dxn. Okay, so 1 over n theta to the n. Take the n plus 1 power, n plus 1, 0 to theta. So what did we get? Oops. Okay, so this n should be in multiplication form. Why did I write it in denominator? I don't know. Okay, so get rid of this n and this n and write in the proper way. Where is it? It should be here, right? It should be here. It should be here, and it should be here. Okay, then what did I get? N over n plus 1 theta. So it's not equal to theta. So this means that expected, or not expected, xn is not an unbiased estimator of theta. But as you can see here, this expectation, the theta here, multiplied by this constant. If we write this constant inside of expectation by multiplying with n plus 1 over n, both sides, then we will end up with unbiased estimator of theta. So if you multiply both sides by n plus 1 over n plus 1 over n xn, the coefficient of theta disappears, so we will have, so we have an unbiased estimator right now. Okay, so this means that n plus 1 over n xn is an unbiased estimator of theta. Okay, sometimes you cannot directly find an unbiased estimator, but here we have a constant only, so we can easily find an unbiased estimator of an unknown parameter using specific estimators. So it will be easy for us. Okay. Let's look at another example. Okay, f of x theta is given as x plus 1 theta square 1 minus theta square. X takes value 0, 1, and the range of theta is from 0 to 1. And here if you calculate, actually get the expectations and things, then here mu is 2, 1 minus theta over 2 here. Okay, so here we calculate MLE of theta as, if you remember, look at the notes before, that we obtain it as 2 over 2 plus x bar, or you can easily get that. And then B MLE of mu is, what is mu? 2 times 1 over theta. Put tilde here to replace this quantity. It should be theta actually. So why did I put? Let me see. Yeah, this should be theta. So theta had here. So 1 minus 2 over 2 plus x bar over 2 over 2 plus x bar here, and at the end we get x bar. Okay, so MLE of mu is x bar here. C. Let's find an unbiased estimator of 1 over theta as a function of x bar. Okay, so here when we check the expected x bar here, we know that it's mu, right? So 2 times or theta minus 1, we can write mu in this form. Then if we want to write theta alone, so what we have to do, write the equation like that, and we will get 1 over theta. So here our aim is to keep this 1 over theta alone. Okay, so divide x by 2, write minus 1 as plus 1 inside of the expectation. So now x bar plus 2 over 2 is an unbiased estimator of 1 over theta. Okay, so let me stop here.